we will find the domain of different types of functions like polynomial, rational, radical, and functions involving fractions with radicals. In almost all of the domain problems, you only need to check the following two rules. First, we cannot divide by zero, because division by zero is undefined. This rule matters whenever a variable appears in the denominator. Second, we cannot take the square root of a negative number, because that is not defined in the real number system. In simple words, the domain of a function is all the possible values of x that you can put into a function f of x, such that it won't break any math rules. Polynomial functions. Polynomial functions are the easiest case. They do not have anything in the denominator, and they do not place anything under square roots. As a result, polynomial functions are defined for every real value of x. We write it as x belongs to R, where this R is all real numbers. In interval notation, this is written as x belongs to negative infinity to positive infinity. We can write it in either of these ways. Rational functions. Rational functions are different from polynomial functions because they contain variables in the denominator. For these functions to be defined, the denominator must not be zero. To find the domain, we look at the denominator, set it not equal to 0, and solve for x. Any value of x that makes the denominator 0 must be excluded. For this function to be defined, set the denominator x minus 5 not equal to 0. Therefore, we get x not equals 5. So all real numbers are allowed except 5. To write the domain in the interval notation, first represent it on a number line. A number line helps to clearly visualize which numbers are included and excluded from the domain. This is shown by an open circle at 5 and then shading the left and right of 5. So, in interval notation, first write the left part as minus infinity to 5, and then write the right part as 5 to positive infinity, and put a union in between. Note that this curved bracket means the number 5 is not included in the domain. Sometimes you will also find a square bracket, which means the number next to it is included in the domain. Then again, note that parentheses are also used for negative and positive infinity, because they do not represent a specific point on a number line. Now for this function to be defined, x squared minus 9 must not equal 0. Factoring this quadratic expression using the difference of squares formula gives x minus 3 times x plus 3. Then we set each factor not equal to 0. This shows that x cannot be equal to minus 3 and x cannot be equal to 3. Therefore, the domain of this function is all real numbers except minus 3 and 3. On a number line, these values are shown with open circles. Now, shade the number line from negative infinity to negative 3, then negative 3 to 3, and then from 3 to positive infinity. From this number line, the domain can be written as negative infinity to minus 3 union minus 3 to 3 union 3 to positive infinity. The parentheses around minus 3 and 3 indicate that both values are excluded. For the next function to be defined, x squared plus 16 must not equal 0. Notice that squaring any real number always gives a non-negative result. Then adding 16 to that squared value always produces a positive number. Therefore, this expression can never be 0. Since no real value of x makes the denominator 0, therefore the domain of this rational function is all real numbers. For this function to be defined, the trinomial must not be equal to 0. To solve this inequality, first factor the trinomial. Find two numbers that multiply to give 10 and add up to give negative 7. These numbers are minus 2 and minus 5, right? So when they are factored, the expression becomes x minus 2 times x minus 5. Now, set each factor not equal to 0. This shows that x cannot equal 2 and x cannot equal 5. Therefore, the domain of this rational function is all real numbers except 2 and 5. From this, the domain can be written in interval notation as negative infinity to 2 union 2 to 5 union 5 to positive infinity.